Hello everyone, today I'll be talking about automatic verbal depiction of a brick assembly for a robot instructing humans. I will start with the context, then the architecture, focusing on the planning and verbalization modules, continue with the experiments and the results, and finally conclude. The context is HRI, and its success depends on having a good understanding between the human and the robot, so sharing goals, intentions, values, and desires. We'll be using multiple modalities to have a smooth and predictable interaction, so the idea is to have a multimodal human-robot interaction in shared tasks. We'll be adopting an assembly task as our problem, which has a large branching factor, and we'll use an online interaction to guide the user towards the goal. So the general setup will be as follows. We will have a robot and a human agent both working on a shared Lego assembly task. The plan to finish the task is only known by the robot, so the robot needs to communicate the plan to the user in order to complete it. And the human's job is to follow the robot's instructions until task completion. Here's the architecture that we decided. First, we have the human agent, we also have the robot, and we have the shared task. Now, this task needs a plan in order to complete it. This plan is a sequence of action, and it's provided by the planner. Now, everything starts with the controller, which requests what to do next, what action to do from the planner. It also requests the perceived current state of the environment. And then with this information, the robot either applies the action or instructs the human agent to do so. And the loop continues until the shared task is complete. Now, our focus is mainly on the planner and the verbalizer modules. The planner takes in the logical description of the actions, an initial state, and an objective, and it gives out, when possible, a sequence of actions to reach this objective. Using a planner helps us adapt the domain and problem to any given task, and it allows the robot to replan and adapt to unexpected events. Now, our planner includes the use of hierarchical planning, and it also considers visibility, applicability, and hierarchical constraints when selecting or searching for the next action. Now, by hierarchical planning, we mean the use of context, inclusion of informative instructions, giving out reason to why we're applying a certain action. Here's an example of the input we use for the planner. So first we have the initial state, then the objective or the goal state. And here we have the set of rules, which is the decomposition of tasks into smaller and smaller subtasks until reaching primitive actions like placing a certain object on the table. So for example, in order to build an arc, we need to build the first tower, the second tower, and then the bridge connecting both towers. Now, having this action, we still need a way to communicate it to the human agent. That's why we have the verbalizer, which is made out of different parameterized layers, each with its own purpose. The depictor first takes the action information provided by the planner and the current state. It takes charge of all geometric aspects as well as the characteristics of objects in the environment. Then we have the semantic generator, focusing on the context of the task and giving a reason or an explanation to why this action needs to be applied. Then comes the syntactic generator, in charge of the syntax to create a well-formed sentence. And finally, we have the realizer to generate the sentence and the text-to-speech to verbalize it. Now, here's an example of a instruction given in French.
Pour faire un pont, mets une barre bleue orientée est-ouest, qui recouvre exactement le sommet jaune de l'escalier et le sommet rouge de la tour.
Now, this is the sentence generated using JSRealB realizer, and the different variables here act as the different parts of the sentences. For example, what's the purpose, what's the task, etc. And as we can see, using JSRealB, we are able to generate both French and English instructions using the same input format. Now, to evaluate the efficiency of the verbalizer and to find out the impact of introducing context when instructing a human, we did 3 experiments. The first 2 were just to provide us with a ground truth corpus of verbal descriptions and give us the highest and lowest ranked natural descriptions for a given task. And we will only go into detail for the third one, which is a web-based assembly, asking the participants to listen to the instruction and continue the assembly as instructed. And this was to test the efficiency of the AI-generated instructions compared to the natural ones provided by the first 2 experiments. Here's an example.
Pour terminer la tour sud, je mets un cube rouge ici. Pour faire un pont, place une barre bleue orientée est-ouest qui recouvre le sommet jaune de l'escalier et le sommet rouge de la tour nord.
Now, we have 2 hypotheses. The first one, including context, might improve task performance, and that the generated sentences fall in between the highest and lowest ranked natural descriptions. As for the results, 40 participants were equally tested with 4 different instruction styles, the most and least popular natural instructions gathered from the first 2 experiments, and 2 AI-generated instructions with and without the use of hierarchical context. We divide the testing scenes into two parts. The first part is the set having one structure available as a reference. And we see that the best ranked natural instruction outperformed all the rest in terms of time complete, and both best ranked natural instruction and the generated one using context outperformed the rest in terms of successful completion from the human agent. Now, as for the second part, where the scenes had more than one structure as a reference, we had a similar results in time to complete. However, the generated instructions without the use of hierarchical context outperformed all the rest when it came to successful completion. Now, this mirrors the findings of the data collection experiment, where people proposed the use of certain criteria like axes or adding a verification step, but disliked them when they were asked to choose the best type of description. Finally, we asked the participants to do a two-part questionnaire at the end of the assembly. The first to evaluate the different aspects of our verbalization, and the second to evaluate the mental chart. Now, we saw that the instructions were syntactically correct and clear. There were no major ambiguities. They were properly uttered, and both the use and dismissal of context are appreciated by the human agents, even though they were leaning more towards the use of hierarchical context. As for the mental charge, the tasks were required effort and cognitive load. The participants were satisfied with the rhythm and did not express important signs of stress or frustration. To conclude, both hypotheses were proven. In many cases, referring to hierarchical context improved human performance, and the participants were satisfied with the generated sentences that had better results than the lowest ranked natural instructions. As for the perspectives, we hope to apply this one-to-one interaction using a robot, also adding robot gestures like pointing, picking, and placing a gaze while considering eye-speech hand coordination. And finally, considering working with multiple human agents while considering turn-taking and benefiting from partial order planning. Thank you.